Hi, welcome to a new lecture. In this video, we're going to talk about decision trees. To be more specific, we're going to emphasize what are regression trees and classification trees. So let's get started with the concept of decision tree. So in general, this is a model that is highly intuitive. It's very popular because the interpretability is high. Even some consider that this model has higher interpretability than a linear regression model. Now, some of the benefits is that it can handle nonlinear relationships, interactions among the different variables. It works for categorical and numerical variables. Even when you have missing data, you can use this model, the decision tree. There is no need to scale or normalize the features. And we can use them to solve the basic of classification and regression problems. However, there are adaptations to use trees also in time series, clustering analysis, even for anomaly detection. So typically a structure, it has some nodes. So the root node is like the beginning of the tree. And then there are some internal nodes. So we'll see different branches. So typically at each node, there will be a variable, an important variable or relevant variable. So we'll see some rules like if x1 is less than specific value at threshold, let's say k here. So if it's true, so you go in this branch, but if it's false, then you will use the other branch. So again, in the other nodes, you will have now other filters, or sometimes it can be even the same filter, it doesn't matter, it depends on the problem. And there will be a different threshold to compare. I'm going to call this one K2. Same idea, if it's true, you go to the left, if it's false, you go to the right. Now, at the bottom of the tree, you will find the leaf node. Here is where we are going to get the predictions, which are the average value for regressions, or in the case of classification problems, it's going to be the majority vote. It's going to be like which class is more popular in this leaf. So that will give you the prediction, the y hat. Okay, so let me show you some examples to give you a better idea on how these trees work. In this problem, the idea is to predict the blood pressure. That's our dependent variable, that's y, the blood pressure. And we have two independent variables, two futures. We have age, which is here, and we also have the non-smoker, whether the person is smoker or non-smoker. That's a categorical variable. Okay, so our model, our tree, is gonna check first these two variables, age and whether the person is smoker or not, to see which one reduces more the error. So in the case of age, for example, you will find like it will try different like thresholds to see which one is going to minimize the error. So here in the root node, it will compute the mean square error. So in order to do so, the first assumption is that the prediction for each variable, the y hat, is just the average of all observations. It's just the average of all the observations that you have, because there are no splits here at the beginning of the tree. So you will get something, I don't know, I guess it will be around here between 12.5 and 13, most likely, right? The average for the whole data set. And with that y hat, which is an average, it will compute errors. It's just each observation, right? The distance of the error, y minus y hat, square, and then it finds the average for that. That's the mean square error, for the whole data set, assuming that the y hat is just the average of the dependent value, of the dependent variable. So now we're going to try to minimize that mean square error by finding the threshold. So the algorithm is going to try different values for age, and it will find that here at age 50 is where it's going to minimize the mean square error. So at this age, for values or observations that are below age equal to 50. So we get these observations. So we will make a prediction of the average of these values, right, for those observations, and it will compute the error for those. The mean square error is just the distance between each value, the real value, the y, and the average, which is the y hat, the prediction, right? Now I will do the same, for observations that are above, right, above or equal to 50. So you will compute the mean square. The average will be here. The average will be somewhere in this area, right? And you will find the distance between each observation and that average. That will be the residuals. Like you square the residual, you find the mean square error for that side of the tree, right? So the idea is that the split at 50 is reducing the mean square error, right? That's the whole idea. That's why the tree is going to pick this threshold, this value. And it makes sense because if you compare, you see like observations that are below 50 and observations that are above or equal 50, the mean values, they are very different, right? And that's fine because that's the idea. We want to differentiate them. We want to be able to fit all possibilities. Okay, so now for the observations that are below 50, there is no need to do more splitting because it's not possible. You see that the other variable, it's mixed here, right? It's not possible to make more splits in this area. I mean, the average here is fine to predict these values, regardless whether the person is a smoker or not. Only in this region below 50. Now, in the region greater than equal 50, is different because we see that there are some differences here, right? So that's why the tree is going to add another node in this region, and it will ask whether the person is smoker or not. If it's smoker, if it's yes, then the predicted value is this one, 14, which is the average of those observations, right? The smokers. But if the person is not a smoker, then the false means that the y hat is the average of this observation, which is 13, right? So you can see clearly that there is a difference here. So this is how this works. This is how the regression tree works. It's gonna make some splits for the different variables in order to fit the data, even if it's non-linear, because here, if you see it's non-linear, if you try like a linear regression, it's going to be difficult here to fit all these observations. You won't be able to capture the pattern, but the tree here will be able to do that. So for the regression tree, the purpose, the goal is to minimize the mean square error, and the predictions are just the average values in my training set. Of course, following the branches, the nodes, until you get to the leaf. So when you follow that path, right, that will be the prediction for that. If there is a new observation, let's say that we're given a new observation here, and for that observation x1, which is age, let's say is 30, and x2, which is the person is smoker or not, let's say that it's a smoker, yes. So when we input this information in our tree, so x1 is less than 50, yes. So the prediction is just 12. That's how it works. Okay, in the case of the classification tree, we don't use mean square errors that for regression, but here there are like two popular metrics, the Gini impurity and also the entropy. So let's use the Gini, which is the default in scikit-learn. So the idea here is that we have some observations and there are multiple classes. Here we have 4 different classes and we want to classify them. We want a model to classify. So the tree is picking 2 variables, the color. So it's going to ask if it's yellow or not. If it's yellow, then you go to the left. If it's not yellow, then it's false, then you go to the right. So it starts classifying, right? Separating the different animals. And then it's going to ask about the height. If it's greater or equal 10, then the prediction is the animal is going to be a giraffe. But if it's less than 10, then it's going to be a tiger. Now, in the other part of the tree, it's going to ask the same thing, the height. So if it's less than 10, then we have a monkey, that's the prediction. If not, then you have an elephant. Now, since we don't have the mean square error here, how does the Gini work? Let's try to understand a little bit more this metric. So the metric is 1 minus, and the sum of this P that you see here is the proportion of each class, or in this case of each animal in the node. For example, here we have, remember that there are 4 classes, right? For different animals. So for the giraffe, the proportion will be, okay, out of these animals, how many are giraffes? So we have 2 out of the 4 animals over there are giraffes. That's the proportion, that's the PK for giraffes. For the tigers, there are 2 out of 4 too. But then for the other classes, it's just 0 and 0, right? There are no monkeys and no elephants because there are 4 classes, right? So in this node, we have 0.5 of the proportion 0.5, 50% are giraffes and 50% are tigers. There are 0% monkeys and 0% of elephants. So that's the PK. That's the PK here that you use in the Gini metric. Let me show you how you can measure it. Here we have some examples. So let's say that in a node, you have two classes, class A and class B, let's call them. So 100%, if 100% is class A, that means that you have like perfect separation in that node, right? So that's why the Gini impurity is equal to 0, because 1 squared, that's 1, plus 0 squared, that this sum is equal to 1, y minus 1 is equal to 0. So Gini impurity of 0 means that you will have a perfect separation in that node. So you can classify almost perfectly, like if you follow that path in your tree. Let's see this example when you have a balanced binary. So here's when you're not doing a good job. You have, like 2 classes and they are equally separated. You don't want this because you want to make predictions. When you're creating the trees, the idea is that we want to be able to predict. So we want to create differences. So we want a small Gini. We don't want a high Gini. But if we have this case where they are evenly distributed, like 50% of the observations belong to class A and the other 50 belongs to class B, then in that case, the Gini is going to be 0.5 squared plus 0.5 squared, 1 minus that, that's 0.5. So this is the maximum value that you can get. That's the maximum value that you can get. And we want to minimize this. We want to get this value close to 0. Because when you take this value close to 0, that means that you are classifying, that your tree is able to separate, is able to differentiate the different classes. Let's see this example. When we have in the node 0.8 and 0.2, 80% and 20%. So in that scenario, the Gini is decreasing a little bit, right? It's 0.32. Now, how we know that we want to minimize the Gini, like close to 0, but how we know if we're doing a good job when we're splitting, right? Or at least the tree, when you have a classification tree, there are algorithms that are gonna, perform the splits, but how the algorithm is gonna know is doing a good job. In order to do so, it's gonna compare the Gini of the parent node with the child nodes. Remember that in the tree we have splits, so we have a node here, and then based on a variable and a threshold, we get 2 child nodes, right? Child 1 and child 2. So in the parent node here in the example, we have 6 observations from class A and 4 observations in class B. The Gini for that is 0.48. I mean, using the equation, right? 0.48. Now, doing the splits, let's say that we get this distribution. So child 1, this node, 4 observations belong to A, 0 to B. And the Gini here is 0, which is good. It's doing a good separation. It's classifying. For the child 2, the Gini, it's 0.445. So we need to find out the weighted Gini for these childs, right? The weighted Gini. So we'll only consider the proportions, like how many of the observations go to this one, to this child 1, and how many observations go to child 2. So to child 1, we have 4 observations, and in child 2, there are 6 observations. So that's why the weights are 0.4 and 0.6. And when we compute the weighted Gini, it's 0.267. 0.267. So the Gini gain here is the reduction in the Gini. So initially in the parent node, the Gini was 0.48, but now in the child's, the Gini is 0.267. So this difference is the Gini gain, right? So the higher the gain, the better, right? Because we're splitting and we are able to classify better an observation. This is very important to this concept of the gain, because you can see the importance of a future, because you're using a variable here to make the split, and if the gain is high, that means that that variable is important, because it reduces in this case the Gini. If we're doing regression, it's going to reduce the mean square error. Okay, trees, they are known because they have high interpretability, but they have some problems. Typically, they will overfit your data if you allow the tree, to run freely. You need to specify the hyperparameter to regularize the hyperparameters to avoid overfitting, because these are high variance models and they are very sensitive to the data. So the data changes, even small changes will change your tree completely. That's possible. So some of the important hyperparameters, the max depth refers to the maximum number of levels or layers that the tree is allowed to grow. So let me show it to you in this example. So we have here one level, level 2 and level 3. So here, if I say max depth 3, means that for this tree, it won't be able to make more splits, like to create another level here. That won't be possible. So the max depth is going to control that, right? Like, then we have the max features, which is the maximum number of features that are evaluated for splitting at each node. Remember that in our original problem, we have multiple variables. So the model needs to check, different variables at each split. So we can minimize, we can reduce or control the number of variables that we check. So you can say 3, only 4, or a proportion will work too. Okay, max leaf nodes. So maximum number of leaf nodes that we're allowed to have. Mean sample split is the minimum number of samples a node must have before it can be split. So for example here, you can say, you cannot make a split unless you have at least 20 observations. So if it has only 10, then it won't be able to make more splits. That's the meaning of the mean sample splits. Mean samples leaf is the minimum number of samples a leaf node must have to be created. This is in order to make the predictions, right? You have to be careful with this one, because if the number is too small, it will overfit. Because if there is, let's say, only one observation in the leaf, then the predictions will be based on a single observation. And that's not good, because you won't be able to generalize. Okay, so you can increase this hyperparameter that have the minimum value for the mean, or you can, if you increase or if you reduce the max of the hyperparameters, you can regularize the model. For the future importance, as I mentioned when I was showing the Gini examples, so the idea is to measure how important it's a variable in our tree. So typically, important variables will be on top of the tree. That's true, but that's not the only way to see it, because it's possible that even a variable that is not, like in the root node, it's possible that that variable, let's say that it's in the middle of the tree, it's the most important variable in your model. So the only way to measure that, it's finding the impurity reduction. Remember the Gini gain that we found? That's a delta. So when you have a parent node and you have child 1 and child 2, so with regression, you will compute the mean square error here, and also for the childs. If it's classification, you will use Gini, right? So the whole idea here is that you compute whatever metric we're using for the parent, Gini or mean square error, and then you will remove the Gini or mean square error of the child's, right? Using a weighted average, basically. So that distance or the difference will give you an idea of how important is the future. Now, it is possible that a single future it's in different nodes in the tree. That's possible. That again, that the same variable is in different nodes in your tree. So if that's the case, then you will need to sum the gains of the the different splits for that future, and then you will normalize across all futures. So you compute the importance. Of course, the higher this value, then it's going to be more considered more important in your tree. Okay, so what are the advantages and limitations of using trees? In general, I would say that you should use trees if you are dealing with a regression problem or a classification problem. I will use them even during the EDA, in the exploration of your data, in the exploratory data analysis. I will use trees for sure to identify patterns that you cannot see in traditional plots, scatter plots, box plots. Trees are very useful in your EDA. Now, for prediction purposes, they are not the best tool. Typically, they will be outperformed by random forest, like all these Bayesian and boosting techniques. But again, it's really useful because you can, given the high interpretability of trees, you can get good understanding of the problem, a good understanding of the variables and the thresholds. So I highly encourage you to use trees for EDA, or even when you are comparing models, like just to get some baselines. That's fine. But in general, you will find better models for prediction. For interpretability, no, it's not going to be that simple because these ones are really good for interpretability, but not that good for predictions. So the limitations, you gotta be careful because they tend to overfit. So remember, you need to regularize the hyperparameters. So they are unstable. Small changes will generate different trees as possible. It's not, in general, it's not an optimal global predictor, as I was saying before. It's more for interpretability, understanding, even in business. People without a background in in data science or AI, they will understand if you show them a tree. If you explain the tree, people will follow. It's not going to be the same if you have a neural network. It's going to be a little bit more complex for people to get the idea. So in general, we have typically we talk about the bias and variance trade-off, but there is also another trade-off, which is the accuracy or the prediction error, right? And versus interpretability. So we want to find a good balance. And these models, trees, are really good with interpretability. Okay, so what are our conclusions here? Decision trees they are very intuitive, they are easy to follow, the visualizations are clear. I highly encourage you to use them during the EDA for sure. For predictions, they are not that strong compared to other models. You gotta be careful because they tend to overfit because these are high variance models. So you need to regularize, control the hyperparameters, the max depth, for example. That's critical here. So in practice, decision trees are not used as a standalone solution. Typically, they will be more as building blocks of, like bigger models. So we can use them either by using bagging or boosting strategies, which we will cover in our next video. Okay, I'm going to stop this video for now. I'll see you in our next video.